Good day, everybody. Another way of stating what we're trying to prove today is that 24, we use this vertical bar. I've heard it called, I think, just bar, yeah. 24 divides p squared minus 1. Now, very few people that I've seen like to envelop this in parentheses, but I do. It's the one's kind of dangling out there. Most context says you don't need the parentheses probably, but I think this is the way another way to state it. Multiple of 24 or 24 divides the object means the same thing. Okay. Now notice what's useful here is that this would be if and only if 3 divides p squared, and I'll drop the convention just in the name of brevity here, parenthesizing this, and 8 divides p squared minus 1. That's what we'll be showing today. It's really quite simple, or fairly simple in my opinion. Now, notice I said without. I'm very fond of modular arithmetic. Another way of stating this in a modular arithmetic context would just be to say that p squared is congruent to 1 mod 24. Okay, and this is what I mean by modular arithmetic. Okay, this is a statement in modular arithmetic, and the benefit of this is that you get to treat this congruent symbol, this triple horizontal bar, much like equality. But then there's a lot hidden behind if nobody's ever learned it, they don't trust it, and so a lot of people just prefer to do it this way. Okay, now just one quick example. Let's look at 11 squared. Notice that 24 divides p is a prime, so we'll make it the prime of 11. So this will be 11 squared minus 1. Okay, and this is equal to 120, right? This is equal to 120, and so 5 times 24 is 120. So that's an example of it working. It also works in the smallest case, which is 5, because 5 squared minus 1 is 24. Now notice, y'all, that we have to start, the prime has to be bigger than 3 because the factors of 24 are 2 and 3. It's essentially the reason 24 is equal to what? 2 cubed times 3. So it only has those prime factors. And so in a way, it's just not big. You have to be a prime number greater than or equal to 5, actually. Okay, now let's get busy with the proof that is non-modular arithmetic in character. Okay, this very first statement here, exactly one of 2 consecutive even numbers, okay, is a multiple of 4. Now that's fairly easy. Let's see if we can prove that. Most people believe that, but I think it requires some proof. Let's do maybe 2k. And then 2 times k plus 1. So these would be consecutive even integers, right? Consecutive even integers. But notice that the result follows from the fact that either k or k plus 1 is even, right? Okay, so one of these has to be a multiple of 4 since k is even. One of k or k plus 1 is even. So you see, you just rely back, you kind of piggyback on that, which is a known truth. Okay. So whichever one, if k were even, this would be a multiple of 4. If k plus 1 were even, this would be a multiple of 4. And exactly 1, okay? And that is exactly, I thought it had to be less than, but it's definitely, because that, if k plus 1 were even, then k would be odd, right? Okay, so that would just be exactly, 2 would divide that number fully, I think is what they call it, okay? So that turns out to be important because, remember, we are looking at, note that p squared minus 1 is equal to p plus 1. That's why we're taking this path. Times p minus 1. Just a very well-known difference of 2 squares. Right? Okay? And that means p plus 1 and p minus 1 are consecutive even numbers since p is certainly odd, right? So this these two numbers, p plus 1, or these two expressions, p plus 1 and p minus 1, are consecutive even numbers. Okay? So that means one of them is divisible by 4, the other one's divisible by 2. So you see, we already have, this already implies that 8 divides, I'll just write it in right here, 8 divides p squared minus 1. And again, folks, it follows immediately from this statement that exactly one of 2 consecutive even integers is a multiple of 4. The exactly, we could say at least, that would be strong enough, but it is exactly. All right. Now the next part of this, so we have 8 divides p squared minus 1. And remember, that's one of the things we were trying to do. Okay, so we have that from here. Now, also exactly one of 3 consecutive is a multiple of 3, right? But notice that p is a prime greater than 3. Remember, p is a prime greater than 3. We can write greater than or equal to 5 if you prefer. P is greater than or equal to 5. So you see, p wouldn't be prime if it were a multiple of 3, right? So either p minus 1 or p plus 1 is a multiple of 3, right? Maybe both, I think. No, just one, right? Yeah, just one. And so y'all, what is it that we've proven that 3 divides p squared minus 1, right? So we have 3 dividing p squared minus 1 and 8 dividing p squared minus 1. That implies that 24 divides p squared minus 1. This time I'll wrap it in parens. Okay? And we'll say QED. Again, Latin for we have demonstrated this. We have demonstrated something like that. So y'all, a very simple, what many would call an elementary proof, right? It's hard to contest any of these things. It depends completely on the fact that 2 consecutive even numbers, one has to be a multiple of 4, and then 3 consecutive integers, period, has to be a multiple of 3. We rule out p because p's prime, right? So that means 3 has to divide one of these, p minus 1 or p plus 1, and that proves it. I mean, that's fairly cool. It's fairly straightforward, and it's kind of relieving to see that type of proof, in my opinion, because you know what I mean? A lot of modular arithmetic is cool. I love it, but I learned it in number theory, and I like it. I like the fact that it confers the notion of equality to the divisibility operator, more or less. There's a little bit of difference because divisibility, I think, is a partial order, I think, you know. But anyway, you get into some theory there. But really, I like modular arithmetic, and I've proven this on this channel with modular arithmetic. But this is a very nice, in my opinion, what you would call elementary, not using anything high powered, no fancy results, Euler-Totient function or anything special. Nothing special is getting used here except fairly things that 6th grade kids who bright at math would understand this proof, because none of the claims are hard to prove. Okay, alrighty, folks. Thank you for viewing.